Hello everyone. My name is Chetan Mittal. Currently, I'm pursuing my MS by Research from Triple IT Hyderabad. I joined Triple IT since 2021 August. Then, after first semester, I joined Dr. G. Abbas as my professor, as a guide of my research. The title of this research, which we started, is all about voltage and current references. The voltage and current references is an analog block. So basically, my research is all about low power analog circuit designs. And now I would like to present my work, which is design and implementation of trim-free voltage and current references for energy efficient IoT applications. Okay. So the motivation behind the low power analog circuits for IoT application. So basically, there is always a motivation, like why exactly we are doing this. So basically, we are dealing with low power circuits. So why low power circuits is important nowadays? So low power circuits are energy efficient circuits. What is energy efficient circuits? So basically, we can improve the lifetime operational lifetime of our circuits with the help of energy efficiency. If you see this graph, as we are reducing the load current, and with the help of reducing load current, we are able to increase the operational lifetime up to 70%. So basically, here we are improving the power consumption by reducing the current. So as we are reducing current, we are able to increase the operation lifetime. At the same time, in terms of cost effectiveness, as we are involving more number of devices into a system, why how we are able to improve the, because as the power consumption is less, so we are accommodating lesser area for a particular devices. So let's say we have x amount, x into x micrometer area. So and now we are reducing the size of a devices, so we can accommodate more number of devices into the same area. So likewise, we are able to improve the cost effectiveness of that system. Then at the same time, we are talking about the scalability, right? As we are able to scale down the tech nodes, at the same time we are dealing with low power circuits where we are scaling the voltage as well. So for example, let's say earlier we require 2 volt supply, 3 volt supply for a particular blocks, but nowadays for low power circuits we are able to achieve the same specification with less than 1 volt. So here we are able to improve the voltage scaling as well. Now we are talking about the subthreshold region for a low power circuits. So basically, subthreshold region is nothing but a friend of low power circuits. So as you all know, MOSFETs operate in certain regions. So in general, we know the region are cutoff regions, linear regions, and saturation region. But there is one more region, that is subthreshold region. So when your gate to source voltage, if you notice, just a second. This is the MOSFET NMOS we are dealing here. If your gate to source voltage is less than threshold voltage, then generally we assume that is a cutoff region. But there is a region when VGS is a little lesser than VTH. That region is nothing but a subthreshold region. At that region, the current that we are getting is in nanoamps or in picoamps. So which will helpful to build the circuit which is low power in nature. Okay. If you see the condition here, here the condition VGS is less than VTH, and the current equation that we are getting is in exponential form. If you remember the saturation current equation, which is in parabolic form, in square law that follows square law, but this I reference equation follow exponential law. At the same time, if you make this VDS 4 times VT or greater, then exponential of minus 4 VT by VT, that exponential term which leads to 0. So the ultimate equation that we are getting IREF is this equation. So this is the main equation that we are using in our research, so that we are able to build a circuit which is low power in nature and at the same time generate very less current. Okay. If you see the comparison also in this table, if the region of operation is saturation, the power consumption and the supply voltage, the power consumption is in microwatt or greater, and the supply voltage is greater than 1 volt. But at the same time, if you are dealing with subthreshold region, the power consumption is in nanowatt or in picowatt, and at the same time, the supply voltage is lesser than 1 volt. So that is our ultimate motivation why we are using subthreshold region. Then the the title of this slide is process temperature and voltage independent analog circuits. So basically, the important aspect of any analog circuit is that the circuit should be independent of process, voltage, and temperature. So how these things are related, I'll explain you. So for example, let's say you are build for example, let's say in this research we are building voltage and current sources, right? So for voltage sources, let's say you are generating out, your output is some voltage source, right? But at the same time, you have to make sure that output should not vary with respect to temperature, with respect to voltage, with respect to process. What exactly temperature? I will give you an example. Let's say you built your circuit in an ambient temperature of 20 degrees centigrade, but at the same time you operate. Let's say you have a smartwatch, right? You are sitting in some cold places, right, where the ambient temperature is 10 degrees centigrade. At the same time, you move to a place where the temperature is 50 degrees centigrade. So your circuit should work with the same proportion, with the same specification at that temperature as well. So that is called a temperature invariant circuit. So here we are talking our circuit should be temperature invariant. So what kind of a variation we have seen in generally analog circuits? So we have three kinds of nature, that is PTAT, CTAT, and CWT. So what is PTAT? Is nothing but proportional to absolute temperature. So let's say when your temperature is increasing, your output quantity, whether it is voltage, current, or resistance, it should proportionally change with respect to temperature. That is nothing but a PTAT. And CTAT is nothing but complementary to absolute temperature. Let's say you are increasing your temperature, your output quantity, that is voltage or current, should decrease with respect to temperature. And CWT is constant with respect to temperature. That means that if you are changing your temperature but your output quantity should not change. That is what our ultimate goal is to achieve. Our analog circuit should be CWT in nature, right? How you will find the temperature variation? We will find the temperature variation with the help of this quantity, that is TC, temperature coefficient. So with the help of temperature coefficient, we are able to understand like how for per degree centigrade how much temperature coefficient it is varying, like how much temperature it is varying. That is nothing but a TC. A second most important aspect of this analog of our analog circuits are supply variation. Supply variation means, let's say you have an analog circuits like, and you have a supply, let's say VDD, you have a supply. So because of noise or other sources, your supply will change from delta V times, but your circuit output quantity should not change with that variation. That is nothing but a supply independent circuits. So that quantity we will what to say measure with the help of line sensitivity. That is, you will check how much maximum it will change to the minimum, divide by the value at which you are achieving the minimum supply into 10 power minus 2. That is nothing but in a percentage. We are calculating percentage, that's why we did this 10 power minus 2. After the supply independent, temperature independent, the most important parameter that we need to look up is process variation. So basically, process variation, it is the variation which we will not mitigate completely, because this variation comes from devices sides. So from when some device engineer manufacture some device, so because of the doping concentration and other aspects, so there may be a possibility that we will get some process variation. But our target is to achieve less process variation, so that we can say our circuit is independent of process as well. So what exactly process variation is? So let's say you have a wafer, right? Whenever you design something, you have a wafer. In your wafer, you have certain corners, right? You have TT corner, SS corner. These corners are nothing but it will tells about the speed of PMOS and NMOS. So let's say you have TT. So first letter will indicate the speed of NMOS. The second will indicate the speed of PMOS. Let's say you have FF corner. FF nothing means fast corner. Means your NMOS is fast, your PMOS is fast. Let's say if your NMOS is fast, that means it will charge very quickly, discharge very quickly. That means the current we are pumping through that capacitor, through that MOSFET is higher. If your current is higher, that means your VTH value should be lower. So that's why for fast our VTH value will decrease. For slow our VTH value will increase. So with that point of view, we understand the important parameter that is that you can say that will affect the circuit, analog circuit, in terms of process variation is nothing but a threshold voltage. So here we are discussing, if you come to the fast corner, your threshold voltage will reduce. If you come to the slow corner, your threshold voltage will increase. So that's how we are able to understand the variation of process. After this, then I'll slowly come to my research, which is nothing but the block that I designed is voltage and current reference. So these are the fundamental analog blocks that we use in general in every IoT based systems. So let's say you are designing a power management IC, you are designing some IoT based designs. For that, you require current source, a voltage source, right? How much voltage you needed, how much current is required for that particular system. So that ultimately comes from the block that is current and voltage references. So if you see, if you see the voltage that we will get from this block is independent of process voltage and temperature that we discussed earlier. This is the foundational block of analog circuit. Here we are dealing with subthreshold region because our ultimate goal is to generate low power circuits. So low power circuits we design in subthreshold, as we discussed earlier. The specification that is needed for any block that is for voltage reference is talking about the temperature coefficient, which will tell us about the variation of temperature. Line sensitivity, it will tells about the supply variation, how much supply is varying, how with the help of as supply is varying, how your circuit is behaving. Then we talk about the process and process accuracy, like if your VTH is changing with respect to corners, how your circuit is behaving. PSRR, power supply rejection ratio, as we are changing the supply, how much output specification is changing. Power consumption and area, these are the specification that is needed for voltage and current reference. Okay, now we are talking about the method of generation of these voltage and current references. So for example, let's say some beginner is there and he or she want to build that voltage or current reference. So how exactly he will proceed? So basically I'll describe in two cases. As case one is about the combination of voltage or current reference with opposite temperature dependency. So let's say if you want to design a constant output of the, whether it is voltage or current, in terms of temperature. So what you will do one thing, you will add the two temperature dependencies terms which are opposite in nature. Let's say you have one, you have PTED current or voltage, and at the same time you have CTED current or voltage. If you combine all these together, then the output that you are getting is constant with respect to temperature. That means whatever it is proportionally changing, at the same time it will decreasing with the same proportion, so that we will get the constant with respect to temperature term. The second combination that we will figure out is, as we are subtracting to same temperature dependencies but with different slopes. If you see, for this the slope is A, for this the slope is B. If you're changing the slope of two different temperature with same temperature dependencies, the output that we are getting is constant with respect to temperature. Same thing we can do for CTAT as well. So these two are uh, so basically we have three methods to generate voltage and current reference: by adding two quantities with opposite temperature dependencies, by subtracting quantities with same dependencies but with different slopes. So these are the three methods we have. Now I'll slowly come to my research side, how exactly we'll implement. So what motivate me to build a circuit which is low, which is low in power, which has process independent, and we are not using any external circuitry to improve those process variations, right? So I start with my research with the state of with some literature survey. So from literature survey, I'll figure out, okay, for some circuit, let's say if power consumption is there, that right, they have high power consumption, they have higher process accuracy, and our ultimate goal is to design low power. So if you see all the specs, so our work, which is I'm mentioning here, which is 37 nanowatt, is beating all the state of art except this 19th reference. But if you see carefully, this 19th reference is using what, native oxide devices. So native oxide devices generally deals with very less current, which is in picoamps. That's why the power consumption that we are getting is 156 picowatt. But the process accuracy, if you see, is very bad, and this comes when after doing trimming. So they are using trimming, and after trimming also the specs that we are getting is not very that they are getting is not very good. So our design is all about power consumption, which we are able to reduce up to a certain extent. The process accuracy that we are getting, that we are achieving without trimming circuits. So basically, I'll give you one more hint about the trimming circuit. Trimming circuit is nothing. Let's say you are getting some process variation. To improve those process variation, we are using trimming circuits so that it will come to a actual state. That's why we are using trimming circuits. But trimming circuit exactly requires external circuits. External circuit means more MOSFETs, more current. More MOSFETs means more cost. So it will increase your cost, trimming circuits. That's why our motivation behind not to use trimming circuit is we want a cost effective circuits, right? So for cost effective circuit, trimming is not needed, and at the same time we are able to achieve a process accuracy up to a certain range, and the power consumption we are getting is very good, right, which is in 37 nanowatt. Now I'm talking about the design that we built. So this design is all about voltage and current reference. So we are building voltage and current reference into a single block. Okay, so if you see the principle of current reference, so let's say you took one MOSFET and you will apply some gate voltage here with some temperature dependency and some drain voltage with some temperature dependency. The output that you are getting is IREF. So so I'll do some experiment. I'll just go through some maths and understand, okay, if we apply CTAT gate to source voltage and PTAT drain to source voltage in a MOSFET, then the MOSFET, the current that we are getting is independent with respect to temperature. Okay. And if you see the MOSFET that we are dealing, that M naught is triode, that we are operating in triode region, so that it will act like a resistor. Okay, we know MOSFET when operating in active region, it will act like a triode, it will act like a resistor. Okay. So if you see this figure, so here this is nothing but a triode resistor based beta multiplier. So this M naught MOSFET is nothing but this. If you see this block diagram, so we have this part as a CTAT generator, this whole part is CTAT generator, and this whole part as a PTAT generator. So we are putting PTAT voltage source here and CTAT voltage source here to get a reference current. Okay. Now I'll tell you the maths behind this current reference. If you see, this I reference is nothing but Kn. So this is the equation of a current when MOSFET operates in a active region or linear region. Okay. So here we have VGS of M naught and VDS of M naught, right? Two things. As I told you, VGS of M naught is CTAT in nature. And as we all know, the VTH, the threshold voltage that we have, is CTAT in nature. So the VGS that we are getting is CTAT in nature. And VDS is nothing but eta VT. VT is what? KT by Q. This is thermal voltage, right? As temperature increasing, our VDS is increasing. So this is PTAT in nature. So we have CTAT voltage, PTAT voltage that we are putting into a MOSFET. The current that we are getting is this, is with this expression. So we have, and we can cancel VTH from here. The ultimate expression that we are getting is this, and with the help of W by L, which is a design parameter, we are able to achieve a reference current. Okay, once we are able to achieve this reference current, the same reference current we are dumping into this PTAT generator, so that we are able to achieve this reference voltage. So what principle we are using here to generate reference voltage is, so we are adding two different temperature dependencies, as I told you earlier, right? So we have one PTAT and this is one CTAT, and if we are adding those two quantities, the output that we are ultimately getting is CWT, constant with respect to temperature. So we have this PTAT voltage and the CTAT voltage. The reference voltage that we are getting is the addition of PTAT plus CTAT. Okay, if you see this, VTH will cancel out. The ultimate PTAT voltage we are getting is here, and the CTAT voltage we are getting is here. So after this, the V reference we are getting is combination of CTAT plus PTAT. So this is the maths behind the current and voltage references. Now there is one more aspect that we are actually dealing, is the process variation. So we are claiming that our circuit is process independent without using any external trimming circuitry. So how we are claiming that, how we are saying this statements. So as you see the expression, this IREF expression contains two VTH terms and they are opposite in nature. So they will cancel out their effects. So in our reference I reference circuit equation, we have no VTH terms present. That means the VTH is the most, you can say, variant term towards process. If you see, I have written also, VTH contribute the most and IREF contribute the least among these process variation. So that's why we are able to cancel this VTH term, so that the I reference that we are getting is constant with respect to process. Same thing I am showing here with the help of simulation also. So let's say I plot VGS minus VTH curve with respect to temperature. Okay. So if you see, this VGS minus VTH is the main term which is present in our I reference equation. Across all five corners, which is TT, SS, FF, SF, and FS, which we discussed earlier, the variation is very minimum, right? The variation is not, you can say there is no much spread across the process. So that's why we are claiming the I reference that we are getting is independent with respect to process. At the same time, voltage reference we are saying is, so for reference voltage, we have VTH term and this eta VT term. So as we know, VTH term is variant with respect to process, but that VTH process variation is mitigating with the help of this eta variation. So how I am saying this is, I am explaining here, as VTH is increasing, as threshold voltage is increasing across, let's say earlier we are on TT corner, from TT2 we move to SS corner. SS corner means VTH increases. As VTH increases, that means current that we are achieving is decreasing with the help of current equation. So as current is increasing, that we are pumping less current into our MOSFETs. That means drain to source voltage also reduces. As drain to source voltage is nothing but eta Vt ln some constant term. So the only term that will decrease with as this VDS is decreasing is eta term. So eta term is also increasing. So that means VTH and eta has opposite dependency with respect to process. As VTH increases with respect to process, the eta decreases, right? So that's how we are able to mitigate whatever variation we are getting from VTH through, with the help of eta. So likewise, we are able to generate process variant design, invariant design. These are the results that I'm showing here is what with respect to temperature, with respect to supply. As we discussed, TC that we are discussing, TC that we are getting is 62 ppm, which is very good. The V reference, TC of I reference also I'm showing here. This is with respect to supply. As supply is changing, but if you see the output that you are getting is constant. That's what our ultimate goal is. This is the process variation of voltage and current reference. That means we will not get much spread across all the corners. Even let's say I took 1000 sample, for the 1000 samples lies acrossly around this voltage range only. And this is the current plot also. This is I'm putting the numbers. These are the results, Monte Carlo results that we are generally showing for process variation and mismatch. If you see, the Monte Carlo results are also promising. So that with the help of those results, we are claiming that our circuit is independent of process. This is the state of art that I'm showing is this work which I am done in 90 nanometer tech notes and other works. So in terms of power, in terms of process variation, in terms of trimming used or not, our circuit, our design is able to beat all the state of arts. After this design, I'll extend my research to, let's say for example, earlier circuit that I showed you, that I was shown is all about current and voltage reference. But there, if you see, the power consumption is in nanowatt, right? But let's say if I want to design something in very less power, and at the same time the current that I want is independent of process completely. Earlier, if you have seen, there is some process variation across some process variation, but in this design we are ultimately trying to mitigate process variation up to a certain extent, right? How we will do it? So for that, so we are dealing with current reference. So we are standalone design current reference this time with different architecture. What architecture we are using here, if you see, so we come up with the some literature survey. In literature survey, we found, so we have a conventional beta multiplier, but the problem is that they are using resistors, amplifier, and the power consumption is very high. To improve the power consumption, we will take high valued resistor. But as we take high valued resistors, means high area is needed. So that's why if you see, the area is higher. Okay. Then we come up with the next topology, that is MOSFET based current reference. But again, the problem is we are able to achieve the, if you see, the line sensitivity is very good, but the supply voltage is very high, and at the same time 300 nanowatt we are consuming. Okay. Then we come up with this circuit. If you see, this circuit has very good power. The power is in picowatt, means ultra low power they are designing. Even supply voltage is very good, है ना? But the problem is they are using op-amp, one thing, and the another problem is they are using gate leakage. And the problem with gate leakage is they are process uh, variant MOSFETs. So if you see the process variation of this topology, which is very high, and they are using trimming circuitry also for that. Then after analyzing all those topologies, we come up with a topology which will generate a very decent power supply, that is power consumption, that is 3.3 nanowatt, which is good in terms of other state of arts. And the supply that we are using is zero point 0.8, which is less than 1 volt. And at the same time, we are able to achieve a line sensitivity of 0.198 with an area of 0.074 micrometer square without using any trimming circuits. Now, what is the idea behind this topology? So basically, we know the subthreshold region equation that I told you earlier. I'll not go much into it because we already discussed this part. So the main novelty is that we discover here is that we found here is, so for example, we know subthreshold saturation region. So when VDS is 4 times of VTH, then this term will disappear, and this is what we are getting in terms of reference equation. What if we put that VDS less than VTH? It's not VTH, it's VT. Sorry, I'll change it. It's VT, thermal voltage. So if your VDS is less than VT, that means this exponential term is now not this numerator is now not dominating, this denominator is dominating now. So if you expand this exponential series, then you will come to know this 1 minus exponential of minus vds by vt will become vds by vt only. So now you have this equation. So how this equation is very helpful. So earlier we have some exponential terms here which will create a non-linearity in terms of I reference. So now we have a linear terms, right? So this vt will cancel out. So we will have, so this current equation that we are having is more control over temperature dependency compared to previous one. So if you see this design and analysis, this is the block diagram that we are using here. Okay, so the concept that we are dealing is the same concept that we are dealing, but here the CTED voltage and PTED voltage is different. So that means here we have a more controlled CTED voltage and more controlled PTED voltage. How I am saying more controlled? So let's say earlier we have this as a CTED voltage, right? So if you change this CTED voltage, then this VGS will also changing, at the same time current will also changing. So we want to make this current isolate, so that let's say we are changing some CTED voltage, it will not hamper our current. So that's why we put this block. So this block will help us to give a control over the CTED slope. Why we are more concerning about CTED slope? If you see, because for current reference we require a certain CTED voltage, right? That CTED voltage slope in terms of temperature I'm talking, we can control with the help of W by L of this circuits. So this is CTED voltage generator that we are using. So the output equation that we are getting, CTED output equation that we are getting, if you see this VGS of MREF is nothing but a VCTED. Here we are giving this VCTED only. We have a more control over slope. If you see that we have this W by L terms we are having. So with the help of this W by L, we are able to control this VGS ka slope, right? And at the same time we have VDS also here. The novel part that I'm discussing here is VDS is this time is less than VTH VT. So earlier if you see, the VTS is 4 times of VT, that means 80 millivolts, 90 millivolt, but this time we are having only 15 millivolt as VDS, which will make sure that this MREF should operate in subthreshold triode region. Okay, that's why we have this VDS only this time. So VDS is nothing but eta VT NNN. How we are getting this VDS term is, if you see, if you apply KVL here, so VGS of M21 plus VGS of M21 is equals to nothing but VDS across this MREF, right? So this VDS equals to eta VT LNN. If you solve this maths, you are able to get this voltage, right? After putting all those, let's say we are putting VDS here, VGS here, we are come up with this IREF equation. If you see, this IREF equation is independent of temperature, voltage and process. That means no temperature term dependent term is there in this IREF equation, no voltage dependent term is there, no process dependent term is there. So that means this IREF is independent of temperature, voltage and process. Now we are talking about the process variation. Okay, how exactly we analyze the process variation? So as we all know, the threshold voltage is mainly responsible for process variation. If we somehow able to reduce this process variation VTH, then the IREF that we are getting is process independent, right? But at the same time, here we have a control over VGS also, right? So we can, let's say this eta has some variation which will also cancel out, right? If you see this eta cancellation is also there. So we have eta into eta minus 1. So earlier we have only eta square, right? Now we have eta minus 1. So let's say if eta is changing with some quantity, this eta minus 1 will reduce, right? So likewise we are able to achieve I reference which is independent of process also. You can also see the simulation curve as well. So with respect to different 5 process corners, the variation is very minimum. Almost the VGS minus VTH curve across temperature is same for all process corners. Now in this design we have also put line and sensitivity enhancement circuits. So what exactly it is? So here we are doing nothing, we are just only subtracting 2 circuit that we built. So we built I reference that I told you earlier. So we copied it, this I reference 1 into I reference 2 with the help of current mirror, but with different W by L, so that we have 2 different W by L, so we have 2 different I reference, right? So with the help of subtractor circuit, how we are subtracting this I reference, putting in this current mirror, this current mirroring is takes place. So this is I ref which is coming out of this. So we have I reference 2 coming from up, I reference 1 is going through this node. So the output that we are getting is I reference 2 minus I reference 1. So we are able to subtract two circuit currents, right? So this is nothing but a subtractor circuit, right? You can see in simulations also, let's say this blue one is nothing but I reference 1, this green one is I reference 2. The I reference final that we are getting is I reference 1 final, which is independent with respect to supply. If you see, earlier one is changing with respect to supply voltage, earlier two is changing very drastically with respect to supply voltage, but the final after subtraction that we are getting is independent with respect to supply voltage. If you see the maths also, so we have here I reference 1 minus P into I reference 2 here, right? So we put some maths here. I reference 1 is nothing but, it's nothing but y equal to mx plus c. So we put only this part. This is this at this time circuit is not working, right? Our what to say, desired region of operation or desired range of the voltage is this much only. So we can consider it as a line, right? So we put the equation of line y equal to mx plus c, y equal to mx plus c. So after subtracting we have this equation. So if you want to reduce the what to say, variability with respect to voltage, then you will reduce this term to zero, almost zero. So that's how ultimate goal is. So if you see the value of P is chosen such that the difference between A and PB approaches zero, so that we will not have any VDD dependent terms in the output reference current. So this is what our ultimate goal is. Here in this paper, in this work, we also put one more technique, that is duty cycling techniques. Why we are using duty cycling technique? As we are claiming this circuit is ultra low power circuit, so we want to save some amount of power also. So what exactly we observed is that the circuit that is generating C-type voltage is not always needed, right? Once we are able to get the seated voltage, if we are able to store that seated voltage in this capacitor, then we are good to off this switch, so that we don't need this seated generator always. So with the help of this technique, we are able to reduce the effect of power that is generating through seated voltage throughout the circuit. So let's say for 1 millisecond or some second, when our this seated voltage is stored in this capacitor, then we will switch off this switch off this we will off this switch, turn off the switch, so that the voltage that we are getting across this capacitor is seated voltage. Then we don't need this block, right? The power consumption throughout the circuit is because of this circuit only. So that's why also I'm putting here, we are putting 1.33% active time. So that means for, let's say, t times, we are only putting 0.133 second. Let's say we have 1 second duration of the whole circuit, then only 0.00133% times we are only on this circuit. Once we are able to achieve the voltage, then we are off this circuit, right? If you see, without duty cycling, the power consumption is 52 nanowatt, but with duty cycling we are only getting 3.3 nanowatt. So that means we are able to achieve a power saving of 94% with using duty cycling circuit, which is very important and very good for ultra low power circuits. Now we are talking about the results that we have with respect to temperature and supply variation, how our output quantity, that is current in this case, is varying. And I'm putting the temperature coefficient value also, line sensitivity values also. And this is the process variation result, that means across the 5 corners, that is TTSSFF. If you see the I reference, that is our output quantity, is not changing much, right? And this is VGS minus VTH curve, which we shown earlier also. This is the Monte Carlo results, which is needed for a process variation. If you see, the sigma y mu value is very, very good. That's why we are claiming this circuit is a process variant circuit, invariant circuit. This slide shows the power distribution. So of 3.3, so 3.3 nanowatt is the total power consumption that we are getting across the circuits. So we are distributing, like how current reference is taking 22%. Likewise, we are distributing the power here. This is nothing but a startup circuit plot that we are showing that at what time our circuit is operating, right? So initially, before 1.5 millisecond, our circuit is not working, but after 1.5 millisecond, we are getting the current, that is our nominal current, that is 593 picoampere, we are achieving. This is the comparison with the state of art. Again, I'm saying with respect to process variation, we are achieving the best results. And the power, that the current that we are getting is 593 picoampere with a power consumption of 3.3 nanowatt only, and with a supply range of 0.8 to 2.5 volt over a temperature range of -40 to 100 degrees centigrade. So this is the specs of our work with respect to state of art. Now, after designing voltage current reference, voltage come current reference, again I'm interested to know, like, do we are we able to implement some voltage reference which is very low in power and which require very low supply voltage. Then we'll do some research, do some state literature survey. Then we come to know ki, for example, if you see this ninth reference, this reference is generating 18 nanowatts power consumptions only, but the process accuracy is still very high and the line sensitivities are not good. So in this work, our main target is a low power, low voltage circuit with a very excellent line sensitivity, and which is independent to process voltage and temperature without using any external trimming circuitry. So if you see this work that we are able to generate 30 nanowatt as a power consumption, 0.96% accuracy, which is very good compared to state of art. Okay, and this line sensitivity, if you see, is 0.0012% per volt. Means 1 volt change, if your output is if you are changing your supply by 1 volt, your output quantity is changing 0.00000012 volt. That is very good actually. And we are not using any trimming circuits here. In the registers, native device amplifier, we are not using anything which will responsible for power consumptions. So this is the motivation behind why exactly we need to design voltage reference with these specs. Then we come to the design concepts here. So this is the basic block diagram that we are doing. So we are pumping a reference current, a I bias current, into a composite pair based structure. But here the bulk of M16 and M15 are different. If you see, the bulk of M16 is connected with V bias and the bulk of M15 is connected to ground only. So with mathematical analysis, V reference is nothing but VGS 15 minus VGS 16. If you if you if you put the VGS value, which is nothing but VTH plus some eta VT term. So if you see, the VTH 15, VTH 16 is not same right now, because the VTH is also dependent on source to bulk voltage, right? This time the source to bulk voltage of M16 and M15 is not same. So that's why we have a variation. Earlier, if this bulk is not there, then VTH 15 is equal to VTH 16, then we don't have this term, right? This term is not here. Then we have only this eta VT terms, which is p-type in nature. Now, to make this circuit independent with respect to temperature, we need to create this VTH1 minus VTH2 as c-type in nature, because this is p-type, right? And according to the method of generation of reference voltage, we need some seated voltage also, a voltage which is opposite in temperature dependency compared to this one, right? So that's what we did is 5 times of this is nothing but a VTH equation, right? So we have VSB term, or VSB nothing but Vref minus V bias. So V bias, where we are generating CTAD in nature, so minus of CTAD is nothing but a PTAD in nature. So minus of so we have here we are generating VSB as PTAD, of minus of PTAD is nothing but a CTAD. So we are able to generate this quantity as CTAD in nature, and this is p-type in nature. So after proper W by L, we are able to achieve V reference, which is independent with respect to temperature. If you see this block diagram, this is our main actual circuit. So the same again, we are using this suggestive based MOSFET, which will generate I bias. Okay, this I bias is pumping into this gate diode connected MOSFET, which will generate a CTAD voltage. That CTAD voltage we are giving, so that I reference we are getting. That I reference we are pumping into this composite pair based circuit. As I'm showing here, I bias we are generating. This is I bias, and we are achieving this V reference. So what is different in this beta multiplier? So earlier, if you see, this is the maths. So before going into this different beta multiplier, I'll tell you the maths behind this. So this is I bias circuit, the equation of current when it is in triode region. The VDS that we are having is this. The VGS is that VGS we are putting is nothing but this is V bias only that we are generating from I bias, that is VTH plus some terms. So if after putting all those VGS and VBS term, we are getting this equation. If you see this equation, we are able to with the help of W by L, we are able to control this I bias to a constant with respect to temperature. So we have a control over W by L, this SMN2, SMN1, these are all W by L ratios, right? So we are able to control this I bias. And V reference is nothing but this equation that we told earlier. So with the help of W by L of Km16, Km15, we are able to achieve V reference, right? Now, I'm talking about the novelty. So basically, we did some improvement in current bias circuit in terms of line sensitivity. So this is our basic structure that we generally use here, and this is another B part is another novel idea. So which is already being used by in some circuits, but our ultimate motivation is low power, right? And if we are using op-amp, then op-amp will consume some, good power consumption, so which we don't want. That's why we'll replace this op-amp into a common source amplifier. If you see the comparison table of architecture also, it without op-amp we are having a 10 nanowatt power consumption with a line sensitivity. This is what our work, that beta media with common source, that is getting 25 nanowatt, which is a reasonable power consumption with a very good line sensitivity. That is what our ultimate goal is. So we are able to remove the op-amp. We are only using common source amplifier here, and we are generating a very less power consumption, that is in nanowatt, with a good line sensitivity. So this is the motivation behind this line sensitivity improvement current bias circuit. Here I'm showing the maths behind this current bias circuit. So if you see this equation, I bias is gm8 times of something in denominator into vdd. So that means what is line sensitivity? I told you earlier, when your supply voltage is changing, how your output voltage or current is behaving with respect to that change. So let's say if this is your supply voltage, if your vdd is changing, let's say some delta amount, the I bias is changing with delta amount divided by some this big term. So the overall variation with respect to supply is very less, if you see. So that is the motivation behind this I bias generator that we are getting with the help of, so with the help of GM, this M11, M10, M9. So we are getting this RM11, R11, GM11. So that will make our circuit more robust in terms of voltage, right? If you see this line sensitivity of voltage reference, so here we are also getting one more term, that gm16 also we are in getting in division. So that means whatever line sensitivity we are getting for I bias, we will get for vref as an improved version, because we are getting gm16 as denominator as well. So this time this denominator is more dominant compared to iref generator, right? So the overall line sensitivity that we are getting for this reference voltage is a good number. This is the result that I am showing here. The TC that we are getting is 23 ppm per degree centigrade. Line sensitivity, which is our novelty in terms of specification, is 0.0012% per volt. This is the Monte Carlo result for process variation. This is also process variation and of voltage reference and PSRR plot. That PSRR plot is nothing but we are getting a very good PSR, that is approximately minus 85 dB. That means it will reject almost all the supply noise that we are getting from outside terms. That we are able to reject. This is the work that I'm putting here. Compared to state of art, the process accuracy is very good. The power consumption, that is 14.2 nanowatts, is reasonably good compared to state of art. The TC, the line sensitivity, the PSRR, all these things are very good in numbers. Area also we are able to reduce up to a certain extent. And we are not using, the good part is we are not using any registers, amplifier or thin oxide devices to achieve all this specification. Thank you.